My name's Mark Miller. I'm a Lucene Solr committer. I work for Lucid Imagination. I'm going to talk a little bit about a couple of the features coming to Solr4. Not going to cover everything, but a few of the things I think are interesting, a few of the things that I've worked on. So I'm going to start talking about the new DirectSolrSpellChecker. Talk a little bit about the new near-realtime support, real-time get, SolrCloud, some of the work we've done in the past on the search side, and SolrCloud, some of the stuff that we're working on now and we're going to be working on over the next few months on the indexing side. So first, the DirectSolrSpellChecker. This I think is pretty cool. In the past, spell checking in Solr involved a separate little sidecar index. That's kind of no fun. There's kind of a build phase where you have to build that little index, so it's not really always up to date. When you're doing distributed and replication, you've got to replicate that around or something, you got to deal with it. In Solr4 now, you're going to be able to do spell check suggestions straight off an indexed field rather than having to build this little sidecar index. That's pretty cool. This work, the history of where this came from, I don't remember how long ago, but a couple years ago, Robert Muir introduced basically this new finite state mechanism to do wildcard queries. Basically, in Solr4, a lot of wildcard queries, a lot of cases will be much, much faster because we're using this new automaton query as the base. So when Robert did that, one of the first things I asked him was, well, can we use this with the fuzzy query as well? In the past, the fuzzy query for Lucene has been completely unscalable. Basically, it runs through every term in the index and calculates the Levenshtein distance. It's pretty slow. It's pretty unscalable. It's always bugged me. I've never had any use for the fuzzy query myself, really. I've never used it. But I really hate that there was this unscalable query that if you had anything but a toy index, it was ridiculously slow. So basically, I talked to Robert a little, and he said, well, we can make this fast. Here's this crazy paper that tells you how to build a finite state machine to do this. It's nothing I'm that interested in, but here's the paper. So basically, I started prodding him, looking at the paper, saying, hey, we can figure this out. We spent a bunch of late nights on IRC kind of hashing it out. We looked around for someone else who had implemented it, obviously in Java, that would obviously make things a lot easier. We couldn't find anything, but we did find this Python library that implemented it. And so we basically spent a long time trying to understand this algorithm. We basically got to the point where we could figure out, for up to an edit distance of 1, we could figure out how to make this thing. It was non-trivial to extend that to greater than 1. And we were kind of headed down that road. But in the end, Mike McCandless, another Lucene committer, he knows Python pretty well. And we ended up using this Moman Python library to generate the Java code necessary to do this stuff. It was a pretty cool accomplishment. And in the end, we ended up with this fuzzy query that's actually scalable, that's really fast. And a little time after that, Robert used that to create this DirectSolrSpellChecker that basically uses the fuzzy query to do loose spell checking. Pretty cool. So finite state machine, if you don't know what it is, I'm not going to really explain it now, but it's kind of a little example. I know David or Dawid, however you want to pronounce it, and he seems to accept both ways. He's talked about this in some of his talks before, but that's cool stuff. So if you want to use it, in Solr config, where you normally configure your spell checker, now for the class name, you just say the new Solr.DirectSpellChecker, goodbye sidecar index. So cool. Next thing I'm going to talk about, real-time get. This was recently added by Bionic. Basically, this kind of lets you use Solr as a little more like a database. When you add a document and then you ask for it with real-time get, as soon as you've added it, you can then request what you've just added, kind of like a database. Whereas in the normal case, you're not going to see what you just added until a new searcher is opened, which can be pretty fast, but it's not going to be guaranteed to be on the next request you make. That stuff's going to be there. With the real-time get, that's possible. Makes things a little more NoSQL-ish. Main reason we added it is we need this functionality most likely for in the SolrCloud stuff when we want to do recovery. You want to be able to ask for the latest document, whether there's been a new searcher opened or not. You need the latest document that's hit that machine. So kind of a little side benefit, though, is you can use this on your own. In the past, when I've written Lucene applications, a lot of times I've had a little sidecar database for fields that, you know, I need that kind of behavior, that once you add something, you want to guarantee the next request that that's going to be there. And so you got to use a separate database. You got to keep things in sync. Sometimes they get out of sync. It's kind of a pain. This is a way to kind of get around that. So to use it, what it does is it takes advantage of the new transaction log stuff that Bionic also recently added. And so basically, when you ask for something with real-time get, first it looks and sees if it's in the transaction log, which is, you know, really quick, really fast. If it's not there, it checks the latest searcher. And so to enable it, you basically first you have to in Solr config. The transaction log is disabled by default. You have to enable it. It's basically just adding that little bit of config there. And then you set up a new request handler that enables the real-time get. This one's called /get. So, you know, you just hit the /get request handler, and got some examples here of what the request might be. This, you know, asks for the results in JSON, and basically just really quick little example. Works the same as you might get stored fields in the past, but, you know, it's real time. So next feature I'm talking about, something that, you know, a lot of people have wanted in the past, near real time. This is something that's recently come to Lucene, and is pretty cool, and so we've been working to get it into Solr. In the past, a lot of people kind of do this usually by juggling multiple cores in Solr, or by, you know, doing things based on time. You know, the stuff that's the newest will be in a really small core so that you can reopen it really fast, and then you've got to move older stuff into larger cores. It's kind of a pain to juggle that and manage it. So a little while ago, I was looking at the update handler in Solr. The implementation was called Direct Update Handler 2. The code in that was getting a little old. It was written when Lucene didn't have a lot of features it has now, so it was written to handle a lot of things that it doesn't need to handle anymore. So I decided it was time to look at that and say, well, how should this work now? Let's kind of you know, look at starting over. In the end, I didn't actually have to start over. A lot of how it was implemented was actually pretty good. I just had to fix a few things. So some of the things I fixed was fixing commits so that they don't wait for background merges to complete. In the past, we closed the index writer on every commit. This normally is fairly fast, but every now and then, if it triggers a background merge, then it waits for that background merge to complete before the commit returns. Sometimes that's pretty slow if you have a really large index. So what would happen is you would commit, and so I've got this here, you know, first commit might take 1 second, second commit 0.5 seconds, next commit 1.2 seconds. People are like, oh, cool, I can basically do near real time. I can, you know, do a commit at least every couple seconds. But then all of a sudden you trigger a background merge, and whoa, that commit took 1.5 minutes. And while you were also, you were still trying to commit pretty fast, so all of a sudden commits are piling up on top of each other, and it breaks down. And that's when most people say, oh, I've got to use another small core to get around this. Kind of annoying. So also remove some unnecessary locking. Lucene kind of handles a lot of things a lot better than it did in the past. So where Solr was doing some locking to manage some features in the past, that's unnecessary. Remove that. Probably improves concurrency a little bit. I added the NRT support. Doing that was a matter of adding what we call a soft commit now. You have the standard commit you had in the past. You have a soft commit. And then I added the soft auto commit. If you know auto commit in Solr, it's basically you can say, you know, every time I add a document within n seconds, I want it to be committed so it's visible. We've got that for near real time now. I'll talk a little bit more about it in a minute. So one of the other things I fixed that really bugged me, we work on a project called Lucid Works for Lucid, and we've implemented some crawlers for that. And so basically, when you're crawling, you're continuously adding documents to a Solr core. And a lot of times, we've got to reload the Solr core when you make config changes. So you might make some search-side config changes, and you've got to reload the Solr core. If you're crawling while you do that, really, that should be fine. The old core should be handling the incoming documents. The new core comes up and continues handling the incoming documents with the new search-side settings. As soon as we started doing that, we realized when multi-core was implemented, there was kind of a little mistake made in that each core creates a new index writer. So you reload the core, a new core comes up, it's going to make its own index writer. Normally it's fine because the index writer is lazy loaded, basically. It's created lazily. So if you're not adding documents continuously, there's not going to be any overlap of trying to open a new index writer while an old index writer is open. But if you are adding documents while that reload happens, you're going to get index writer lock timeout, which shouldn't happen, kind of sucks. So I wanted to fix that. And so basically, the solution sounds easy. You just need to share that index writer across Solr core reloads, obviously. It was a little more complicated to do because of the way replication works. Replication in Solr kind of complicates a lot of the update handler side. But after a little work, a little testing, finally figured that out. And now when you reload the core, it shares the index writer. You can continuously add data and do reloads. It's pretty cool. So the NRT auto commit that was added, now you can basically say, instead of commit, you say soft commit. It does a much faster refresh of the index. You can do that, maybe faster even than once every second. Probably normally you might set it up for once every second. This might be a common configuration you can set up now. You might set up auto commit for 1 minute. So every time you add a document, within 1 minute, there's going to be a hard commit. You're guaranteed that that stuff is on stable storage. There's an fsync done, et cetera. And you might set up a soft commit to happen every second. So every second after you add a document, that document will be visible. It won't guaranteed, if you have a hard crash, it won't guaranteed to be on stable storage, but it'll be visible, and anything that happened up to the last minute will be on stable storage. And with the background merges not happening in the background anymore, you're not going to run into the occasional 2-minute wait. So that's pretty cool. So next feature, I'm going to talk about SolrCloud, search side. This is some work that we did, I don't know, a year or two ago, hard to remember now. But so when we decided to tackle SolrCloud, we decided to kind of take it in pieces. Let's start, with the search side. It's a little bit easier than the distributed indexing side. So we basically said, looked around for something to use. We wanted some central configuration. We wanted to be able to publish cluster state, let nodes read the cluster state. We looked at Zookeeper as a great solution for this. It's Apache licensed. It handles all of this stuff pretty well. And so basically, we built in Zookeeper support to Solr. Basically, how that works now is you'll set up what's called a Zookeeper quorum, which is what's at the bottom here. You can set up as many nodes as you want running Zookeeper. They'll store basically all the configuration. You can see that here under /configs. You can have the Solr config. You'll have schema. It'll also have the state of the cluster here. Under collections, there's 1 collection. There's 2 shards. There's 2 replicas for each shard. It'll tell you what nodes are up. Zookeeper has something called an ephemeral node that basically uses a heartbeat to tell which nodes are up. If a node creates or if a server creates an ephemeral node, and then that server goes down, the ephemeral node will disappear. And Zookeeper also has something called a watcher, so that you can watch those nodes. And if a node disappears, you'll be notified that it went down. So this lets each server know which nodes are up, which nodes that it needs to search. And so all of a sudden, in the past, when you do distributed search with Solr, you have to specify every other shard that you want to search. You give it a shards param with each URL of the other shards, and you kind of got to manage that yourself. Now, as every Solr core comes up, it registers itself in Zookeeper. You can just say distrib equals true, and it will go and figure out which shards it needs to search. It'll build the shards param by itself. It'll load balance across replicas automatically for you. There's a new SolrJ client called, I think, SolrCloud, Cloud Solr Server or something. It knows how to load balance as well. It talks to Zookeeper and does load balancing. when you hit a shard with that, that is also load balanced across the other shards. So pretty cool. Basically, you have fault tolerant on the search side. You have central config. So this is the changes entry for it. SolrCloud added shared central config. In the past, if you had a 100-node cluster and you wanted to change something in Solr config, you had to go to each node and make the same change. Now, with the config in Zookeeper in one central location, you make the change in one spot. You reload each of the cores. They pick up the new config. Pretty useful. Built-in load balancing and basically infrastructure for the distributed side, which is what we've just started. So here's just kind of an example of the Zookeeper layout. Again, you've got a configs node where you can put not only Solr config and schema.xml, but your stop words, your synonyms files, all of that can be shared. Basically, when you start up a core, the core registers itself. You can say, this core should be part of Shard4 when you start up the core, and it will register itself. You'll say what collection it should belong to. Basically, every core that comes up can register itself so that other cores know which ones they need to search. So as we're doing the distributed side, we're kind of doing some improvements on what we've done in the past. Some people have been using that pretty successfully. I know Loggly has a pretty big installation using the search side SolrCloud stuff. I've seen a lot of activity on the mailing list of other people kind of playing with it now. As people are playing with it, we've noticed some issues that we're addressing. So one of the recent things that we fixed is, in the past, we've modeled the cluster as so Zookeeper is basically uses a file system extraction layer. So you can see that here. Looks like a file system. The root node is Solr. Under that, there's a node called configs, and then you've got basically file entries under those folders. So, and you can see, every core is going to register these new nodes in Zookeeper. Well, so to read this, it's a new request on every node. And as you get a huge cluster, all of a sudden, you might have a 100-node cluster. You've got to make 100 reads to Zookeeper. It gets kind of slow. So the first thing we did to try to address that is we started doing incremental update. Just start looking at what nodes you don't have and only read the data for new nodes, or remove nodes that are no longer there, that have disappeared. The problem with this is, all of a sudden, we wanted to add properties to each node. You wanted to be able to say, hey, this node is for searching. This node is for indexing. It's kind of hints to Solr clients that know how to read Zookeeper. And so the problem is, if you change one of those states, it doesn't necessarily trigger a watcher unless somebody has a watcher on every single node. And each node needs to know about changes. So if you're going to put a watcher on every single node, it's basically an n-squared problem of every node is watching every other node. It gets a little complicated. So we're making a change now. Rather than representing everything as nodes in Zookeeper, we're going to represent it in JSON or XML and put that as a data point on one node. So that when you read the cluster state, it's going to be one Zookeeper read. You're going to be reading more data, but it's already, we've done some testing. It's much faster. Some downsides to that is that Zookeeper is made to work with only a little bit of data at each node. By default, it's got a 1 megabyte maximum data size. So your cluster description is going to have to fit in 1 megabyte, although I know you can raise that some. I think that in a megabyte, you can easily fit probably a couple thousand node cluster. And then you can use compression possibly after if we have to, or you can raise that, and we'll see how it goes. But yeah, so basically, to talk a little bit more about how some of this works, one of the nodes we have is called live nodes, where every node that comes up registers the ephemeral node. This lets nodes know which other nodes are down. Like I said, though, this is done by a heartbeat, so it's not instantaneous. If a node goes down for a little while, the other nodes are still going to see it and think it's up. So each node also, as it's doing load balancing, tracks which nodes are actually responding. And if another node doesn't respond, it'll add it to a bad list and stop trying to talk to it for a little while. After a bit, it's going to keep trying it again, unless it notices the ephemeral node goes away. Then it can stop, it can just take it out of rotation. But until that happens, it's going to keep occasionally trying it and seeing if it comes back. So basically, we have two ways to know if nodes are down. You have the master record, and then each node itself kind of tracks it. We do this rather than nodes trying to mark each other down, because that gets kind of complicated really quick as people are marking nodes down when it's just because they can't contact them, but other nodes can. And so this is kind of a simpler way to deal with it. So getting started with SolrCloud, I think we've made it fairly easy. One of the things we're working on is making it even easier so that you don't have to do much config. But so at the moment, this is how you might start your first node. You basically give it a Bootstrap configuration directory. That's where all the configuration files you want your collection to run off are. So basically, you might point it to /example/Solr out of the box. That puts all the example Solr configs up into Zookeeper. You might name that collection config so that if you have multiple collections in your cluster, you can have multiple sets of config files and you can name them. If you don't name it myconf, it'll just default to configuration 1. The -zkrun will start up an internal Zookeeper server. So to make things really easy, we've kind of got two modes with Zookeeper. If you're running in production and you're really serious, you probably want to start up your own set of Zookeeper servers and kind of manage that all on your own. But to kind of get started early, we've got this option so that Solr will fire up the Zookeeper server for you. Makes things a little simpler to play around with and get started. If you're running a small cluster, it might be sufficient for you to just go that way. So basically, that'll start up Solr with Zookeeper, one node. If you go, then we've got a new admin page, zookeeper.jsp. There's actually new admin UI coming. It's got also its own view of Zookeeper. I haven't looked into it too much yet, but that'll basically just show you the Zookeeper layout, which nodes are up, which nodes are down, which nodes make up your cluster, et cetera. So that's kind of the search side. That's gone really well. Some people have used that and taken advantage of it. What we kind of leave to you is how to get the data to each node, how to separate it. The distributed indexing, it's tougher. To do it simply, it's easy. You can do just some sort of round robin mod the number of servers you have distribution. But we wanted something better than that, so we've been thinking about it for a while. We want something that's fault tolerant. We want something that's elastic. We want something that's durable. If you add a document to the cluster and it comes back and says success, we want you to know that that document is definitely there. Unless half your cluster goes down, then maybe we won't guarantee that. But as long as most of your nodes are up, it should be replicated around so that it's likely going to stay. So basically, current vision. This is kind of my vision. A little bit long there, but basically the idea is I want it to be as simple as you start up. You basically say, look, I want to shard my index into 20 shards. And so I'd like it so that's all you have to say. You say, I want to shard it into 20 shards, and then you fire up like 60 nodes, and that's going to automatically give you your 20 shards. And since you fired up 60 nodes, you're automatically going to get 3 replicas for each shard with no extra configuration. The only config you're going to pass is how many shards to break it up in. And then basically you can pick any one of those nodes and start indexing to it. And it'll be replicated around how it's supposed to be. You don't have to think about where you're indexing it to. Just pick a server. If a server dies, you shouldn't lose any data. If a full shard goes down with all its replicas, then and you can't recover them, then you will lose data. But if that's a problem, you make more replicas so that it's less likely. It's kind of the idea. So we're kind of taking this a piece at a time. We did some early brainstorming and planning with a couple of the guys at AOL. They've got a lot of large Solr clusters at AOL, and they're finding it difficult to manage. So they're very interested in the index side of this. So we kind of brainstormed with them. They kind of started working on this document of a plan of what we're going to do. Largely, though, we're kind of taking an issue at a time. A lot of this stuff is hard once you get down into the details. But some of the stuff that we're working on to start is the real-time get, like I mentioned, for recovery. The transaction log, which is needed for the real-time get, eventually maybe needed for durability too. Versions, which we want for optimistic locking and basically deciding who wins on each shard when the same document is updated on different shards. Leader per shard we're working on now. That's kind of the route we decided to go, and talk a little bit about that, more about that in a minute. Auto-assign nodes to shards. The current SolrCloud, you've basically got to, every time you fire up a core, you've got to say which shard this belongs to. We'd like the option of all that happening automatically, where, like I said, all you have to say is how many shards you want, and then it's going to assign, as you fire up machines, it's going to assign them to, you know, if a shard doesn't have a machine assigned to it yet, it'll get one. If every shard has a machine, then new machines will start coming up as replicas, all kind of automatically. And then distributed IDF. If you've used Solr in the past, you know, there's a patch out there to kind of do distributed IDF for Solr4. That method doesn't work anymore. Multi-searcher has been taken out of Lucene in Lucene 4. So kind of the old way of doing distributed IDF doesn't work. We're working on making that possible again. We'll try to get that committed. So versions, this was kind of where the discussion began of how we want to handle, you know, who wins on each machine. If I update a document on one machine, someone else updates the same document on another machine, you know, eventually you want to consistently have the last document to be updated to win. There's different ways to do this, Lampert clocks, vector clocks, or, you know, basically a leader per shard, which is in the end what we decided on. Makes optimistic locking easier, makes a lot of different things easier. So that's the way we're going. So basically every shard and all of its replicas is going to have one leader. We're going to use Zookeeper. Zookeeper is a great way to do leader election. Leader election in the presence of failures is really hard to get right, really hard to do. Zookeeper does it though, uses, I don't know how to say it, Paxos, whatever algorithm. Uses that to do this, uses basically a quorum approach to agree on a new leader. So that allows us to easily version documents because, you know, you've got one leader per shard, all documents go through that leader, really easy to just have an incrementing version, kind of cool. If the leader goes down, there's going to be a new election, new leader comes up. Possibly briefly, you're not going to be able to do an update, or there'll be retries as a new leader is elected. That should be really brief. Kind of in the cap theorem trade-off, we decided not to go with the you know, high availability at all costs. There may be brief times when you need retries, but possibly that'll be built in. So auto-assign shard names. One of the things we're working on now. At the moment, I'm using a simple collection lock with Zookeeper. You know, basically, you need to, as you're assigning shard names, you need to know what the previous assignments have been. So you've got to either have some sort of lock, or you have to have an overseer node that's kind of, you know, basically doing the locking locally to do that, or some sort of optimistic lock where you try to assign something, but if someone else has assigned something, then you back off and try again. I think eventually we're going to go with the overseer method. Rather than the collection lock, where there's going to be, we're probably going to have an overseer anyway, so it makes sense to assign shard names with that same node. And you can use, you know, leader election so that if it goes down, someone else just becomes the overseer and continues on. So basically, this might be a cluster layout. This would be 3 shards, each shard with 2 replicas. Each of the shards is going to have a leader. If you add a document to any of these shards, you can add it to any replicas. Say you add it to this replica, it's going to forward it to the leader. We have kind of the basics of this working in a SolrCloud branch now. It's not fault tolerant or anything yet, but you can add to any of the replicas. It forwards to the leader. The leader's going to version it, and then asynchronously send it back out to each of the replicas so that it's on each of the nodes. So that kind of part is kind of the easy part. The difficult part is going to really be recovery. What happens when a node comes down and then comes back? It's got to talk to the leader and find out, hey, which documents am I missing? What do I need to get to catch up? Versions will come in handy there. I think we're looking at using column stride fields to handle the versions. And so basically, that's the large, hard next step is dealing with all the recovery scenarios. But we've been doing a lot of thinking, a lot of talking about it. So hopefully, you know, over the next 2 months or so, we plan on starting to tackle most of that. So yeah, so these that's a few of the features, kind of more leaning towards the ones I'm working on or ones I find interesting, like the fuzzy stuff, the DirectSolrSpellChecker. There's a lot of other features coming to Solr4. There's pseudo join, pivot faceting, pseudo fields, per segment faceting, configure codec per field, alternate scoring algorithms. You know, you can use BM25 or I don't know, there's like a list of 5 different scoring algorithms you can now configure in Solr, try them out. Robert and a Google Summer of Code guy just added all that. That's really cool stuff coming. When is all of this coming? Not really sure. Whenever we decide to release Lucene Solr4, that's really kind of, yeah, Christmas, maybe. I wouldn't mind Christmas, man. I've been saying, hey, by December, January, let's try to get this out. But who knows? You know, there's this is the 4 release is the first time that we're majorly breaking back compatibility in Lucene and Solr. So it's kind of been a field day of work that's been getting done that was really hard in the past because of how much work you had to put into back compat. So now when we release it, all of a sudden we're not going to be able to break back compat again until 5. So there's a lot of people who want to get, you know, their pet stuff into 4 before we release it. Otherwise, it's a long time before you can really do wild stuff again. So it's going to be difficult to get it out. There's a list kind of that various people have of what they want to finish, but hopefully soon. Some links to some of the stuff I talked about. Yeah, Mark Miller, Twitter, blah, blah, blah. That's my talk. Any questions?
I have a concern concerning the losing the data in Solr. Let's say in a company where I'm working, we have 4 racks with the machines, something like 100+ machines, and we are thinking of installing Solr on them. And let's say that I have 3 or 4 replicas of each shard. You are thinking something about rack awareness? The stuff that Hadoop has. That means if I'm putting replicas, that I'm putting at least 1 replica in a separate rack, and if I'm losing that rack, then I'm sure that I won't lose all replicas. Maybe you can put in Zookeeper additional property for each shard, saying, okay, in which rack that shard resides. I can use maybe that property also when I'm doing searching, that I am using the replicas that are close together.
Right. Yeah. So basically, the question was, you know, can the SolrCloud stuff be rack aware, data center aware, so that, you know, if a whole rack goes down, you don't lose, you know, an entire shard and all its replicas. You want to put maybe replicas on different racks. And so the answer is, I mean, out of the box, the properties for each node, I think we're going to make completely configurable. You can add anything you want. They can act as hints to whatever reads Zookeeper. So you'll probably be able to put that in there right out of the get-go. I think longer term, we want to do more out of the box that works with you know, making things data center aware, rack aware too. I think we're going to do more on that. But properties in general are going to be completely user configurable. You can add any property you want if that helps with whatever you're doing. So.
I guess it was back in at Berlin Buzzbirds, you were talking a little bit about the difficulty of doing sharding and getting scoring to actually work really well within this. Are you looking at this at all in this context? You did mention the IDF problem. Can we go into more depth about that?
Yeah. So I mean, if your data is not kind of completely randomly distributed across shards, then, you know, if you're not using global IDF, you can have a problem. If you have, you know, one kind of data on one shard and another kind of data on another shard, and you're merging results and doing the IDF and scoring calculations locally, you're just going to get kind of wacky results sometimes. So, so we're going to address that by basically doing global IDF. It's going to add basically another phase to the distributed search that collects stats from each shard and creates global stats that you score with. Part of doing that work is we're probably also going to have to do search releases. At the moment, the distributed stuff, if you are doing searches, you can do once, you know, it's multiple phases basically where you talk to each shard. If the searcher changes in between those phases, that can also kind of be wonky. And now that we've added the near real time, where searchers are changing much more frequently, that's kind of more of a problem. So another issue we're working on is short-term searcher leases, where you can say, hey, keep the searcher around for the next second or 2 seconds so that each phase can hit the same searcher. But yeah, I mean, unless things are completely randomly distributed, it can be a big problem. So we're working on that now.
And basically the plan is to release that in Lucene 4?
Yeah. Robert and Andre are working on global IDF right now. So.
Hi, Mark. You mentioned the distributed inverse document frequency. Does this solve the general problems of comparing scores from different slaves?
I'm sorry, say that again?
You mentioned the distributed inverse document frequency on your slides.
Yep.
And my question is, does this solve the general problem of comparing document scores from different slaves?
Right. So I think not across different queries, it doesn't solve that problem of comparing scores, but across different slaves, right, it does, yeah. Basically, it's going to use the global stats for the calculation of all the scores rather than isolated stats and then merging those scores. So yeah, they should be comparable as long as it's the same search.
About the slide you showed with a cluster with a line and column, how does the role of each instance fit in? I mean, for searchers and indexers, for example, could we have 2 lines of indexers and 5 lines of searchers, stuff like that?
So
to avoid to search an index on the same core.
Right. So the question is, how to rephrase it? I guess how we're going to handle different roles for the different nodes. You might want some that are searchers, some that are indexers. That's going to be the per node properties, which will either act as hints or, but usually hints. Probably you're not going to have to respect them. But basically, you know, this node might be labeled an indexer. This node might be labeled a searcher. Then if you're using a smart client, like the cloud SolrJ client, it's going to say, when you're adding documents, it's going to say, hey, I know this one is for indexing, so that's where I'm going to index to. And it'll say, hey, this one says it's for searching, so that's where I'll send my searches to. Basically, you're still going to also be able to talk to each node like you can regular Solr, so you're going to be able to get around that. But the hints will be there, and if you're using a smart client, it can respect those hints and only index at the right spots and only search on the right nodes.
Josef Neumann from ICZ Czech Republic. Mark, may I ask you, could you comment the position between the new real-time search in Solr and the Elasticsearch? Because it's a completely independent community, as I understand, the Elasticsearch versus the Solr.
Yeah, I'm not super familiar with Elasticsearch, but I do know, I mean, we're basically doing the same thing. We're using Lucene's near real-time search to basically open an index reader off the index writer. And that avoids doing fsync, it avoids flushing deletes, and it's just a lot faster. But I mean, it should be completely comparable. It's basically just taking advantage of the NRT support in Lucene.
I have a question. If there's a facet with many different values, and normally if you have facet limit and you're not using sharding, then it can potentially use very little memory. But if you use sharding and you need to produce, well, you need to do faceting on that field with many values, does it send all the values through the network to get result back?
All right, faceting question, that's Yannick. Can you repeat that question too? I don't know.
In distributed mode for faceting, basically say that you're faceting by author, right? You can actually miss values if you know, somebody with the last name of Z appears once on every shard and you just ask for the top 10 on every shard. You'll never get, you'll never hit the Z, right? But it'll actually sort of be in the top. So we do a couple things to try to get around that. One thing is we over-request by a certain amount by default in distributed mode. And the other thing that we do is we do guarantee that whatever counts you get back in distributed faceting are correct. So it is possible to miss a constraint, a facet value altogether, but we do, there's a second phase that basically, you know, if one node did return with a Z, with that Z or something like that, and we didn't hear about it on the other nodes, there'll be a second phase to go and true up the counts and say, okay, I didn't hear, you know, what is your count for this? And so the counts that you get back are guaranteed to be accurate.
Thanks a lot, guys.
Thank you very much.